And it may seem like I'm throwing an unnecessarily complicated word your way just for the hell of it, but this is really the same as saying tangent line. All right, we know how to write the equation of a tangent line. We've talked about it throughout the course. It's come up on every test, for better or for worse. So now we're actually going to do something with it. What's the purpose of these tangent lines? Why are we learning about them? Well, hopefully this either will flesh that out for you. And you know, even if I didn't tell you that, you look at the picture and you see we have a curve, y equals f of x, and something that looks very much like a line that is touching that curve at exactly one point. So if that's the case, then we can assume that that would be a tangent line. All right? And also it says tangent multiple times. All right, so we have this model here. It's a very fancy looking equation, but it's really not that bad also, because if you really dive into what's going on here, we have an a value, and then, so this is some particular constant along the graph corresponding to a. So this is really an x value on the graph. All right, f of a, whenever you evaluate a function for a particular value, you're finding the y value that goes along with that. So this is the y value at the given a. All right, and then the last little ingredient here would be, let's make it purple. Okay. That would be this guy. It's a derivative, f prime of a. That's going to be the slope at a. So if you match those ingredients up with the point slope form of a linear function, you see it's very similar. You know, it's a little out of whack. You know, the point slope form would be y equals m times the quantity x minus x sub 1 plus y sub 1. So y equals m times x minus x sub 1 plus y sub 1. This is the tangent line equation. I mean, it's a line equation. We just use it to find the equation of the tangent in this course. And you can see it has the same ingredients. We have an x value, a y value that goes along with that x value, and a slope. Right? So this really is the same model. All right? So the skills necessary to come up with this L of x equation, for some reason it's L of x now instead of y, the skills necessary, they're nothing new. So that's good news. The L just stands for linearization. Right. The rationale behind linearization has to do with really computer science more than anything else, because if you were to write a program, and how often are we going to do that? I don't know. We did a little bit of it in this class with the calculator, but actually real programming, there is no function for derivative. You know, so you can't just say input an x value, input a y value. Now, do calculus. You can't. The program software is not going to understand that. But what it will understand is simple arithmetic: addition, subtraction, multiplication, division. Programming also has trouble with radicals, powers, and things like that. But it can think in terms of the four basic operations. Right? So what this allows technology to do is calculus with simple operations: addition, subtraction, multiplication, division, right? Provided you could give it a slope. If you can give it the slope and some coordinates to work with, then it can take it from there. And in fact, that's where things like your math 8 on your calculator, intersection function, zero function on your calculator, it's all rooted in this idea. Right, because your calculator doesn't understand symbolic notation, but somehow it can give you a derivative at a point. what it's actually doing is following this idea. It's coming up with a linearization model and giving you a very, very good approximation of the solution. Right? It's not actually doing the algebra behind the scenes. So when you say find the derivative of y equals x squared at 2, it doesn't use the power rule and then plug the 2 in later on. It actually comes up with a very good approximation of the derivative and then plugs in the 2. Right? Because all it can understand is addition, subtraction, multiplication, and division. Right? And that's basically all technology. That's why when you go to Wolfram Alpha to do your math homework for you, anybody know about that, Wolfram Alpha? No? Oh. Well, okay, well, we're all honorable people, so that's great. But if you go to Wolfram Alpha, you could type in pretty much any question and it'll spit out the answer. And if you pay a little bit more, it'll tell you all the work that goes along with it, and graphs and things like that. But when it does the calculations, it does a little spinning, the little pinwheel thing, because it's running the numbers behind the scenes, but it's still not doing algebra. It's not applying the product quotient chain rule or anything like that. It's not looking up its index cards to remember the rule for inverse trig derivatives. It's doing something like this. And then coming up with models that correspond to the numbers, the data, the raw data that comes back. All right, so it's all rooted in this idea. All right. So you want to have a sense of how your calculator might find something like the cube root of a particular number. Like, how does it spit out these values? This technique will actually get us going in that direction. All right. So we have a model, and all we're really asked to do is find the equation of the tangent line. All right. So how hard could that be? Well, it could be immensely difficult if you're given a challenging function. But if you're given f of x equals the cube root of x, which I'll write as x to the 1/3. I just need to find the derivative, which would be what? Exactamundo. It's saying to find all of this stuff, the linear approximation model, so all the stuff that goes with that formula at the x value of 8. Right? So when they give you this piece of information, they're telling us that x is equal to some a value. That's our a value. All right, so that 8 is going to take on the role of a. It's like I scribbled it out. Like, that sucks. All right, whatever. Just pretend I highlighted it nicely. All right, so I would need f of 8 and f prime of 8. Now, you can use your calculator, because I've told you this all along. You can use your calculator whenever you want. You can use it to do the work for you. In this case, it sort of defeats the purpose to use your calculator, because this is to give us a sense of how one might go about finding the cube roots of these numbers without just simply typing in the cube root of 25 in our calculator. We're trying to get a sense of how the calculator does the math. All right, so you really want to kind of put yourself in the calculator's shoes. Right, so you are the calculator. All right, on a test, you see, I'm going to say that repeatedly. I'll try to stop myself. It's relevant in every other class. On a mid-unit assessment or an end-unit assessment, that is not a test. A graded assignment on any grade.
Are there going to be quizzes?
Little tickets here and there. I mean, I'm not. One thing I'm not. I don't like being disingenuous. I'm not going to tell you we're going to stay away from unit tests and then give you period-long quizzes. You know, that's not a lot.
That's one of my notes, which is a freshman year. She was like, "Oh, it's only a quiz, you guys, and I'm longer."
And it was a 100-point quiz, right? Yeah. And the test, the corresponding test was like 20 points. Yeah, I've been there before. I'll never give you a midterm, but then they give you a 300-point test. You know, so anyway, the idea behind this, so when I'm looking for the cube root of 8.05, the cube root of 25, what I want to do, unless they, in this case, they gave me the x value of 8, I want to choose a convenient value as a that's very close to the number that they're asking me about. All right, so in this case, they gave it to us. They told us that x is equal to 8, so the a value is equal to 8. Right? But if they just told me to find the cube root of 8.05, I would be looking for the nearest perfect cube to 8.05, which would be 8. Right? That's why 8 was selected here. If I had a choice, when I'm looking for the cube root of 25, I would be looking for the nearest perfect cube to 25, which would be what? 27, yeah. So that's kind of the idea behind it. But anyway, the cube root of 8 is what? 2. The derivative part can be a little trickier, but these problems are designed for you to be able to come up with the answer without using a calculator. All right, so I'll rewrite it because in this case it's going to be a little bit easier if I rewrite it. 1 over 3 times 8 to the 2/3. If I take 8 and raise it to 2/3, it's the same as taking the cube root of 8 and squaring it, which would be what? 4 times the 3 would give me 12, so 1/12. 1/12. All right, so back to our formula, the L of x formula. You may look at that and say, or at least have the same thought that I had. Do I need to know this if I already know that? If I know that linearization is just finding the tangent line at a point, do I need to use this notation? Absolutely not. Right? So this is textbooky. When you're sitting in a calc class next year, your teacher might say you have to use this. But if you know that this is equivalent to this, I value that knowledge. So go for this. I mean, if call it L of x if that makes sense to you, but y is fine for me. Y is always fine. Y and f of g of h of x, whatever, it's always interchangeable. All right. So if you want to use this model or that model, it makes no difference. Anyway, we have everything we need to come up with a linearization model. I'll write it both ways. If I'm using L of x, it would be f of a, which is 2, plus 1/12 times x minus the a value, which is 8. If I was going with classic tangent line notation, it would be y equals 1/12 x minus 8 plus 2. And as you can see, it's the same equation, just commutative properties work. All right, so that's our linearization model. Now we want to approximate the values of 8.05 and the cube root of 8.05, and then also the cube root of 25. So I'll use the y one.
If they didn't give us 8 as the a value, would you use 8.05 or 25 as the cube that you work with?
If they didn't give us the 8 for the first one, for the 8.05, I would use 8.
Okay.
And then I would do the whole thing again using 27. All right, so these are my two calculations.
Wait, what does the cube root come in?
These linear models represent the cube root function instead of actually using the cube root function. Because you got to be asking yourself in all cases, what's going to be easier to work with? A complex polynomial function, cube root function, trig function, log function, or a nice linear function? I mean, I threw the word nice in there, so obviously it's a linear one. Right? So that's the idea. Right? So we're doing all of this work to replace the complicated function with something much simpler. Right? There are drawbacks that we're going to see in a second, but there are drawbacks that we can work around. So if I plug in 8.05 in for x here, what do I get? Just for the binomial. 0.05. All right. Now I'm going to go with fraction form, just because it's going to be easier to work with. 0.05 is equivalent to what fraction? 1/20th.
Oh, Oh, 5.
So 1/20th times 1/12 would be 1 over what?
1 over 240.
1 over 240. So 2 plus 1 over 240 would be 2 and 1 2/40th. All right. So that would be an approximation of the cube root of 8.05. So I could put it in my calculator, 8.05 as a cube root, that. Not bad, right? Pretty spot on. I mean, it loses it after a little while, but if you think about it, when you use the intersect function on your calculator or numerical derivatives, sometimes it would give you like 2.99999 when it should give you 3, right? Instead of saying, I don't know, like E, which would be 2.718, they'll give you 2.717924. It's very close, but not quite. It's because it's using linearization, and so it creates a little bit of error, but not enough error for you to lose sight of what the true value is. All right, so we got very close, very, very close. Like 1/10,000th off. 1/100,000th off. So not bad. But that's because 8.05 is very close to 8. But 25 is nowhere near 8. Right? So if I put in a 25 here, I'm going to get 17/12ths, right? That's 1 and 5/12ths. So this would be like 3 and 5/12ths. I just fired that off real quick, so I'm not 100%. -5 8 is 17. 17/12ths. So the ones with 5 left over? So 1 and 5/12? I think it's right. Okay, so if I were to try to do the cube root of 25, I got 2.92-ish. 3 and 5/12ths, I don't have to put that in to know that it's not close to 2.92. All right, I mean, it's in the neighborhood, I guess, but it's closer to 3.5. All right, so depending on how accurate you have to be with your approximation, this could be a problem. All right, so what we get as a conclusion here is the closer your required value is to the number that you're plugging into your linearization model, the better off you're going to be. The problem is if you can't evaluate your linearization model or your derivative for that particular number. In this case, it required a perfect cube in order to work out. So I was limited. I had to use a perfect cube. This demonstrates that for the 25, I didn't choose the best perfect cube. So if I did this whole process again with 27 and then ran the numbers again for 25, I would get a much, much closer approximation. Right? And that's illustrated, I think, very nicely by the graph, because you don't need a proof to tell you that near A, you have a little interval around A where your approximations are going to be pretty not bad. It's pretty spot on. But as you move further and further away from A, you can see that there's a pretty large disparity between the red curve and the blue line. All right. So that's for a cube root function, which differentiation-wise, taking the derivative, it's not too bad. Trig functions, they can get out of hand pretty quickly. So here it's saying find the sine of pi over 4. Now we know that sine of pi over 4 should be equal to root 2 over 2. But just like the calculator can't do, or it can't handle symbolic notation for power rule, quotient rule, and things like that, it also doesn't do trig the same way you might think. Right? So the calculator doesn't know unit circle. That's why when you type in the sine of 30 degrees, it gives you 0.5 rather than 1/2. If you type in the sine of 45 degrees, it gives you 0.7071 rather than, radical 2 over 2. All right. So it's actually using an approximation technique, and this is the root of it. The good news is, the unit circle, if you know it, at least the angles around the unit circle, you can identify convenient values close to whatever the number is that you're asked to approximate. Right? So here I'm looking for pi over 4. So 0, that's a convenient value. I mean, they're telling us a convenient value. You might choose something different. I might go with pi over 6 because pi over 6 gives me a clean number. All right? But just because it gives you a clean number for sine doesn't mean it's going to give you a clean number for cosine. Pi over 6 for sine is 1/2. Pi over 6 for cosine is √3 over 2. If you want to avoid radicals, you want to stay on your quadrantals. Right? So the x-axis, y-axis. Because for sine or cosine, it's either 0 or 1. If you get anywhere away from the x or y axis, now you start getting into those radicals. Just because it's clean for one doesn't mean it's going to be clean for the other. So 0 is a nice one. If they didn't give me that, I might choose it anyway. All right, so follow the model. They're using theta here instead of x, but that's not a big deal. If you want, you change it to an x. Nobody's going to lose any sleep over that. So, but I like making theta, so I'm going to leave it that way. All right, derivative of sine is? Cosine. So I need f of 0 and f prime of 0. Sine of 0 is what? What's the y value at 0 radians? 0. What's the x value at 0 radians? 1. All right, I'm going to assume that people probably like the y better than the L of x. That's fine with me, but I'm going to write the y. So slope 1, x minus the a value plus the f of a value. So y equals x. All right, so that's telling us that for the sine function, for values that are close to 0 radians, the x and y values are roughly the same. Once you start getting away from that, they start changing. All right, so if I'm asked to find the sine of pi over 4, my approximation method is going to tell me find y of pi over 4, which would be pi over 4. All right. So pi over 4 in decimal form. I mean, I know what it's supposed to be. It's supposed to be radical 2 over 2, which is about 0.7071. You type it in, sine. All right, so just the pi over 4. It's in the same neighborhood. All right, but pi over 4 is fairly distant away from 0. Right? If I were asked to find something like, maybe it wasn't pi over 4, maybe it was the oft-used pi over 12. Not really, it's not. Let's say it was, instead of pi over 4, it's pi over 12. I would get that number. Closer. Right? Maybe it's pi over 144. That's a number that should be pretty close to 0. I get that. Right? And obviously, if it is 0, then it's perfectly accurate.
So shouldn't it be like an approximate sign, not an equal sign? It's not actually equal.
What is the approximate
Oh,
value?
alright, well, I saw the equations, it was equal sign.
Oh, up here?
No, I'm just saying, in the actual equation, it just says equal to, and it's not the approximate sign?
Oh, here.
Yeah.
Oh, because this is an approximate model,
Okay.
you can use it in an equal sign. It's representing approximation wholly. All right. So,